Hello everyone. So today we're going to start on 5.3. So 5.3 talk about this concept called directional derivative. But before we get to talk about that, let's um, do a little recap first. Let's say given a function, let map from R f that map from Rn to R1. We know that this function f has n partial derivatives. And we understand that this partial derivative, which is called df over dx sub k, basically represent the slope of the tangent of the x sub k coordinate curve for the function f. And because it represents the x sub k is related to x sub k coordinate curve, it has the effect that you only allow x sub k variable to change, which therefore basically have the geometrical effect of meaning the following, meaning that df over dx sub k actually measure the rate of change when move in the x sub k direction. Now, show you how that works. So obviously I would not be able to draw you an n-dimensional surface in Rn plus 1, but I could draw you a two-dimensional surface in R3. So let's do that. So example, suppose I have a function f that maps from R2 to R. And let's say this function is z equal to f of x, y. So the input are x and y, and output is z. And of course, we already know that this function, it represents a two-dimensional surface. So I'm going to just call that surface in R3. So show you how this works. So imagine that's how this surface look like. So once again, this surface will probably be infinitely large, so I won't be able to actually show you what it look like if I don't draw some kind of boundary. So I'm going to kind of draw some kind of boundary to it. So let's say this is my surface. So here's my z equal to f of xy, some kind of surface, and I purposely draw it so that it's on the positive side of the xy plane. So maybe I do this to kind of trick your brain into thinking that like okay, it's kind of over the z-axis. Okay, so that's the surface. What I'm going to do is I'm going to define a point in the domain. So here's a point in the domain. Remember, our domain is the xy plane. So I'm going to define a point in the domain. That point is going to be called x sub 0, y sub 0. And this point corresponding to a point on the surface somewhere. It doesn't matter where, but I'm going to just say right here. And that corresponds to this point x sub 0, y sub 0, f of x sub 0, y sub 0. So that would be the point on the surface. Now, you probably remember seeing this picture. What if I now draw a line parallel to the y-axis that go through the point x sub 0, y sub 0? So that would be the line x equal to x sub 0. Then this line would correspond to some kind of curve that kind of go left to right, just like this red line. And similarly, if I now draw a line that go, let's say go front to back, and this line would be y equal to y sub 0, and then that would form some kind of curve that go front to back of our surface. So remember, these two things are called coordinate curves. So this one that have a fixed x value is called a y coordinate curve. And this one go front to back in the x direction is called the x coordinate curve. So in a sense, if you think about object moving, you can then think of, what if I take the point x sub 0, y sub 0 and move along the line x equal x sub 0? Meaning when I do that, I'm changing the y value. Then this point on top would basically move along the red curve on the surface. Similarly, if I start from the point x sub 0, y sub 0 and move along the x direction, which means changing the x value but keeping the y the same, then the point on top would then move along the x coordinate curve forward and back. So if you think about it essentially, then you can think of it as the derivative, the partial derivative, basically indicate the rate of change in the specific direction. So in this picture right here, you can think of that df over dx is basically the rate of change in the x direction. Because allow you to move along the y to y sub 0 where you're changing the x value. And then df over dy is basically the rate of change, or if you want to think of it as the slope, in the direction, in the y direction. Good. So here comes the question. What if we don't want to move just in the x direction or the y direction? If you think about it, notice the following. If I'm at this point, x sub 0, y sub 0, I can definitely move along the blue line in the x direction, or I can move along the red line, which is the y direction. But what if I want to move not in those two directions, but in this direction? A direction defined by vector v. Now, important to understand that vector v is still on the xy plane. Then what happened is I'm basically trying to form a new curve that can go from x sub 0, y sub 0, but not along the two coordinate curve, but can go in between the two coordinate curve. Now, geometrically speaking, I mean, I should definitely be able to draw a curve that's other than these two curves, the red curve and the blue curve, that go through the point x sub 0, y sub 0. As a matter of fact, if you think about it, shouldn't there be infinite number of curves that go through the point x sub 0, y sub 0? And you're correct. And each of those curves would correspond to a different direction, vector v, that's on the bottom. Because there are also infinite different directions to move from x sub 0, y sub 0 to any other point. You know, indicated by vector v, which vector v could be anywhere. Could be any direction. So therefore, realistically, I should be able to move this point x sub 0, y sub 0, not only along the blue line or the red line, but along a specific direction, which in this case represented by the green arrow. And if I do that, wouldn't that also have some kind of rate of change that we can measure? And of course, there is. The question is how to calculate that. That is what we try to figure out mathematically. So that concept is called a partial derivative with respect to the direction v. So what we're looking for is this. If we move in the direction of v, the question is how to calculate the rate of change. If df over dx is the rate of change in the x direction and df over dy is the rate of change in the y direction, then I should be able to pick an arbitrary direction between those two and still be able to find the rate of change in that direction that I choose. And so that's what we're going to try to figure out. So what we're looking for, it actually has a name. This rate of change is called the partial derivative with respect to the direction v. Partial derivative with respect to direction v. And the notation for that is df over d vector v. And that's the notation. And notice that it does use the partial derivative scripted d because it is a partial derivative. Remember, the derivative of f is called gradient. We learned that in 5.2. So this is basically a partial derivative of that. Okay? And notice they have a vector v on the bottom to indicate that's what direction we're differentiating. So how do we actually calculate this partial derivative? So the definition for df over dv is the following. It's given by this expression. Its limit t approaches 0, f of vector x plus t times vector v minus f of vector x over t. And that's what equal to df over d vector v. Notice the expression looks strangely similar to our definition of a regular derivative, except that we don't have a plus h, but we have plus t times vector v. The idea here is that basically indicate that this basically say if I take a position vector x and I move slightly in the direction of v, and I use it to calculate the slope, what would the slope be? Now, as you probably suspect, we're actually not going to be using this definition too often because, I mean, remember, we don't like to use the limit expression to define the derivative because that's too complicated to calculate. So we do need some quick way to evaluate it. And this is what it is. Okay? To calculate df over d vector v, we can use the gradient vectors. And here's the relationship. df over d vector v is actually equal to gradient of f dot product vector v. So that is the formula that you want to memorize. Now, as with any other formula, so make sure you understand the differences between these two things. One of them is df over d vector v of vector x. That will be equal to gradient of f of vector x dot product vector v. So this become a function. But there's a second notation, which is this, df over d vector v evaluated at x sub 0, and that will equal to gradient vector at x sub 0 dot product vector v. So this one is a vector, a specific vector that being evaluated. Okay, so make sure you understand there's a difference between the two. So just like last unit, I usually call the top one the grade the function, like the gradient function versus gradient vector. Now, show you how this works. So actually pretty straightforward. So imagine the following. Imagine I ask you to do this. Yes, I'm going to show you something next to it. Suppose I have this function right here. Let's say f of x, y, z is equal to a very simple function, x, y squared z to the third. And all I want to do is I'm going to ask you to find the derivative, partial derivative of f in the direction of v. Where v is equal to 1, 2, 3. Actually, you know what? Because of the way I write down the power, I'm going to make it 3 to 1 instead. Just make it easier. 3 to 1. So that means we're looking for this derivative, df over d vector v. So how do you calculate this? Well, simple. We use the formula right there. Notice that this does not give us a vector to evaluate, meaning we don't have x, y, z. We just have the direction of which we want to take the derivative. So we are actually looking for a function. So to do that, what I need to do is to first find the gradient vector. So let's see what the gradient of f is. So gradient of f would be basically the partial derivative of this with respect to x, partial derivative of that with respect to y, and partial derivative of that with respect to z. So it shouldn't be too hard to figure this out. So that means gradient of f of x, y, z would equal to, and sometimes I just put gradient of f without the parentheses x, y, z, because once again it's understood that it has to have input in it. Would just equal to, let's say, y squared z to the third. Df over dy would be 2xyz to the third. And then df over dz would be 3xy squared z squared. Alright, so that's my gradient. So therefore now I can actually find df over d vector f, d vector u, d vector v, I'm sorry. So that would equal to basically gradient of this, so therefore would be y squared z to the third, 2xyz to the third, and 3xy squared z squared. Dot product, the direction 3, 2, 1. Now notice what happened. When I dot product these two things together, it should come out to be a single scalar. So that single scalar is given by this formula. 3y squared z to the third plus 4xyz to the third plus 3xy squared z squared. So 3 times this plus 2 times the middle term plus 1 times the last term, and they all add together. Now, one thing I do want to show you is the following. What if I want to evaluate this? So let's say I want to evaluate at a specific point. Let's say now the next thing I want to do is this. So maybe I will call this A, and I'm going to call this B now. How about evaluate df over d vector z at the point, let's say 1, 1, negative 2. So that's pretty simple. All you have to do is just simply plug those different into this equation and then solve for it. So therefore, in this case, I will have df over d vector v would equal to, if I plug in negative 2 for z, that's negative 8. Negative times 3 is negative 24. Plus, the x and y are both 1, so therefore they stay the same. So 4 times negative 8 again, that would come out to be minus 32. And then plus 3 times negative 2 squared, which is 4, so plus 12. So therefore, sim to me is negative 44. All right, so that's how it goes. Now, however, interesting is the following. Notice this. What if I now ask you for this? Same exact function. So I'm going to ask you to find the derivative of f in the direction of vector v, but this time I'm going to give you v to be this. Now, notice the interesting thing here is that 642, technically speaking, is in the same direction of 321. I simply just double 321 to get 642. Therefore, I'm actually finding the derivative in the same exact direction. But notice what happened to df over d vector v. So df over d vector v would equal to gradient of f dot product v, which basically would just equal to this thing. And therefore come out to be this. Notice that that is not the same thing as what we got before, even though I'm finding the same exact direction, derivative at the same exact direction. Now, if I want to evaluate it, you also notice the following problem. Let's see if I want to evaluate, in this case, evaluate df over d vector v at 642. I'm sorry, not 642, but same exact point, 1, 1, negative 2. Then you'll notice that df over d vector v, and yes, someone would probably guess, wouldn't the value be double? And you are correct, it would be. It would be this plus negative this plus this, which come out to be this. Now, notice the reason why I did these two examples side by side, because I want you to understand that in this case, the way we define this derivative with respect to a given direction has a fundamental flaw in it. And that flaw is the following, is that when I define, even though the same exact direction, in this case, both v are the same direction, but because they have a different magnitude, it changes our derivative and as well as the value that we got from the derivative. And that is a problem. So how do we fix that problem? Well, simple. The answer is the following. The reason why this becomes an issue is because we try to use a vector to define a direction. But a vector defines two things together, a direction and a magnitude. So what we're going to do is try to just use the vector to define the direction and disregard the magnitude. And to do that, what we have to do is simply use what we call a unit vector. A unit vector have a unit length 1. And if we all use the unit vector, we will all have the same exact vector to define this derivative with respect to a given direction. And when we do that, we define something a little different. It's called directional derivative. So notice what we found before is a partial derivative with respect to a given direction. But if we want it to be called directional derivative, we have to satisfy something additional to it. And this is what it is. Let's say given a function f that met from Rn to R1. Let u be a vector in Rn if the length of vector u is equal to 1, therefore indicate that vector u is a unit vector, then the derivative in the direction of u, df over d vector u, is called the directional derivative. This is unique because every direction vector defined, if I normalize it, we all have the same exact direction vector. It's called the directional vector, a directional derivative of f with respect to vector u. So it's called directional derivative. And you can only call it a directional derivative if the length of the direction that you use is length 1. So therefore, neither of these two answers that we found are called directional derivative. They are just derivative in a specific direction. So how do I actually find this? Well, let's go and give it a try. So let's say I have this function f of x, y, z is equal to xy squared z to the third. And now I'm going to ask you to find the directional derivative of f in the direction of So how is that different than all the other problems that we've done? Well, it's right here. We now specify that what I want is a directional derivative. And therefore, in order for it to be a directional derivative, I must have direction in with length 1. And I'm pretty sure vector v doesn't have a length 1. So therefore, the first thing I'm going to do is the following. So vector v is 3, 2, 1. I'm going to now try to find vector u, which is length 1. And to do that, I have to basically take vector v divided by the length of vector v. So that will be 3, 2, 1 divided by the length of vector v, which is 9 plus 4 plus 1, which is 14. So square root of 14. Or I can think of it as 1 over radical 14 multiplied by 3, 2, 1. So now I'm ready to go ahead and form my directional derivative. My directional derivative df over d vector u, which is equal to gradient of f dot product vector u. So in this case, would basically just be what we found before. So let's see if I can write that out. Y squared z to the third. And what is that? 2xyz to the third. 2xyz to the third. And then 3xy squared z squared. 3xy squared z squared. Dot product 1 over radical 14. 3, 2, 1. So therefore, this df over d vector u would come out to be 3 over radical 14 y squared z to the third plus 4 over radical 14 x y z to the third plus 3 over radical 14 x y squared z squared. That is a directional derivative because of the fact that we have a length 1. And if I ask for a directional derivative of this function to this given direction 3, 2, 1, everyone will have the same answers. Because the directional, the unit vector would all be the same. All right. So that actually technically is it for 5.3. So we'll continue on to 5.4 in the next video. All right. I'll talk to you guys later. Bye-bye.